All right, so let's get started. So, so far we've, in this lab that you've done, the net logo lab that you're working on right now, on the last lab, we've started to see ways in which stochastic modeling can enter into simulation. So, as an example, in the inventory model, where I just kind of gave before, you want to model the demand that comes in every day, but you have no idea how many refrigerators are going to be sold every day. Rather than coming up with some weird mathematical model for exactly, based on the weather and things like that, how many refrigerators are going to be sold every day, we instead say, well, let's just look at the stats. And if you look at the statistics of it, then it turns out that it looks like there's kind of a bell curve where on average you sell 4 refrigerators a day. Some days there's a dry spell, you got none. Other days you might be lucky enough to get 8 or 9. But usually it sticks around 4 plus or minus, 2 or 3 or something like that. So you get kind of a distribution around that. And you realize I don't actually care why it looks that way. It tends to look that way. And if it's reliably looks that way, then I can just substitute in a probabilistic model for the demand. And that makes it much easier for me because then now I only have to worry about, say, the mean and standard deviation. And then I've got my demand for any day that I want. I don't have to worry about all the other variables that could go into why people buy more refrigerators on one day or another. So that's kind of where, and we've seen that, that in the net logo models as well. There's opportunities to introduce randomness in how often someone, say, in the segregation model, there's, when you could imagine, so right now in the segregation model, if an individual is sitting at a particular location, a patch, and the number of patches next to them don't match up to that type of individual, then that individual can move. Well, you could imagine saying, well, not that, whereas in net logo that's implemented deterministically, you could imagine making it probabilistic, where you could make the probability that you decide to move depends upon the number of individuals around you, but and it ends up being a relatively simple model where you just count up the number of individuals around you, map that to a probability, flip a coin. If that coin that's weighted by that probability comes up heads, you move. If it comes up tails, you don't. And that ends up turning a decision about whether to move from one location to another, which probably depends on a lot of things, into a decision which depends only on one thing, but still has enough variability to allow slop for the things that you've left out. So that's kind of the 2 ways to look at this, is that either we're using probability just to make our lives easier so that we don't have to add in a bunch of other variables and we end up getting something that's just as good, or we use probability to kind of model this, what we're leaving out. So you may not know all of the factors that are involved in why someone would decide to move from one place to another. But if you account for the things you think are important, you use the variability around them to sort of allow for noise that deals with those variables that you haven't included in your model. And so both of those different approaches must involve us knowing a little bit about probability to build these distributions. And so this is hopefully a little bit of review, but maybe makes it a little bit more rigorous than where we go in 380 and 385 in how we define probability and random variables. Probability is the flip side of statistics. Statistics is all about how do I go from data and make an inference about the data. Probability is going the other way. How do I model something using probabilistic distribution? So probability doesn't necessarily involve any data. Once you get data involved, that's kind of statistics. And so statistics is going from data to a model. Probability is kind of going from like a model out. So we'll hopefully get kind of a better idea of that distinction as we go on here. All right, so here, make sure that we're up and running. All right, so brief announcements. So starting with next week, that's lab 5, that's the first arena lab. So it's a good idea, as the TA mentioned in his announcement, if you're using your own computers, to get arena on your own computers. There's some installation instructions are on Canvas. Also, I've provided you the textbook, but if you would like a hard copy of the textbook, now's a good time to have the arena textbook. The exercises that we do in most of the arena labs are usually modified versions that start with something in the textbook. So you'll have to have access to that textbook to work through those. Homework B1 solutions are available. Of course, there's ICAs that are available. There's homework C2 is available. It is due on the day of lecture D2, which is Tuesday, this next lecture. There's random number generation. There's some content in it that will require a little bit of book reading. So in order for me to get 2 homework assignments in before the midterm, I had to sort of take some of the what I viewed kind of easier content that you can cover yourself and load it into homework C2 before we cover it in lecture. We will end up seeing in lecture, but I kind of point at exactly the exercises they're modeled on. And a bunch of people have already turned in homework C2, so it seems to be working okay. But there is stuff in homework C2 that we haven't covered in lecture yet, but we will, but it'll be due before we actually get to that. The reason we do that is so we have room for the next homework to get in there, which is on random variant generation, that so that I'll have a chance to get that homework completed and solutions to be released to you before the midterm. So a couple of clarifications. There's this A mod B notation down here. If you're not familiar with this modulus notation, A mod B, let's see if I can point this way, that'll make it a little easier. A mod B there, that just means A divided by B, take the remainder of it. So that just is a fancy way of saying remainder when you do A divided by B. Make sure to show work. So on question 1, include formulas for your calculations of each step of those random number generators. If you do it in a table, then make sure you tell me kind of the formulas that you're using in each table cell, so it's clear that we know how you went from one cell to the next. Similar to question 2, if you summarize your results in the table, indicate the formulas you use in table headers, and there's the book example of how to do a problem like question 2 does that just like that. So just some quick clarifications on that. Then, like I said, homework D2, that is now available. There was an old version of D2 that I think accidentally became available a little bit early, but I've updated it for this semester. And so that is available. This one, again, just to make sure for the midterm, it's technically due at a particular day, but I'm going to effectively waive the late penalty for it. So even though it's, I leave the due date, but with the whole 4-day buffer, like I do on all the other homework assignments, as if there were the 20% per day late penalty, but you can turn it in without any late penalty as long as it's available. So that 4 days that comes after the due date, that's usually there for the late period, that's actually extra time you can turn it in without any penalty. And so I do that because I want the solutions for homework D2 to be able to come out with a couple days before the midterm. So you definitely have these solutions available, but there is no way that I could get the solution set to come available. There's no way for me to kind of do it the way I normally do and still have room for everything. And so that's the reason why it's technically due, I forget what, like a week before the midterm, but then of course it's available for 4 days after that. And then the solution set comes out on a Sunday and the midterm is on a Tuesday. And so, so that's just something to keep in mind, that you can use the availability date as an effective due date for this homework. There's this, the other kind of new thing is this Canvas activity F is a midterm review Canvas activity. This one draws random questions from previous ICAs, and you can complete it multiple times and it'll take the highest score. So this is meant to just be a review exercise that helps you review all the stuff we've covered up to this point. So that's kind of there. It is due before lecture F, which I think is the Thursday before the stage 1 exam. Lecture F will be a review session where you can come with your questions, or I've kind of just picked out what I thought are the greatest hits of the lectures that have come before, and I've got them kind of there just to kind of go through, just to generate ideas for questions. But we could spend the whole time doing questions or working things out on the whiteboard or whatever. And so that's kind of up to you, but I make this ICA due before that lecture so that the ICA kind of exercises some demons as you're doing it. However, once that it's due, there will be a practice version that comes out after that, that that you can't complete for credit, but it's exactly the same form. So you still can use it as an online kind of studying tool for the midterm if that ends up being helpful for you. All right, and then like, this is kind of hinting that the midterm's only about 2.5 weeks away. So this text here, this kind of needs to be, well, I think I don't bother to update this because I'm hoping someday we won't be in a pandemic. But so of course this is modified a little bit. So we know that the midterm stage 1, I will be here during normal class time on that day, that Tuesday, but you don't have to come to class to take the midterm. It's a totally Canvas-based midterm. You can bring a laptop here and take it, or any time that day during that 24-hour period, you can choose to start the midterm from remote, and you'll get, I think, about 90 minutes. It's the 75-minute class period plus 15 minutes for any technical issues. And so you can just start that 90 minutes whenever you want. It doesn't matter to me. It could be early in the morning, it could be late at night, just as long as you complete it before the end of the day. That will be your stage 1. And so that's, and then stage 2, that will be on the date that we pick for stage 2 in that survey that's still available until Friday. And then that stage 2 is a little bit similar, but in that case, you get to collaborate and it's not timed. So you just get the full 24-hour period, and you can keep coming back to that exam all day if you want, making changes and all that. And the stage 2 exam is identical to the stage 1 exam. So there's a lot of like administrative details there. Are there any questions from in person or online? And I'll get to, there's a question about the homework online. I'll get to that in a second. Any other questions? Yeah. If you, for the campus-based one here, so I mean, I ultimately, if it flags anything, it comes to me. Like I'm the kind of one that, so if you take it here, it'll be fine if it says like, oh, I see other people in there, because then when I review it, I'll say, oh, well, I know that he was here, and so no big deal. So I'm not one of those professors who, like, if Respondus flags you, you immediately get points off or something like that. I gotta go back and watch them all, because it's so sensitive to a bunch of different things that it's really just a tool to help me as I go through and kind of do the online proctoring. So don't worry. Try not to. I mean, in some ways, I feel conflicted even using Respondus, but it's kind of the lesser of several different evils that, in order to make things work over multiple time zones and things like that. So I will give you a lot of flexibility with that. So try not to be too anxious about the Respondus setup. If there's somebody, if there's a dog barking in there, or somebody's having a conversation over there, don't freak out. It's not, your whole exam isn't trashed because somebody was, in the next room over having a conversation. So none of that. Any other questions before I handle this homework question? All right, so online I've got, for the homework, can we use Excel for the first one, or do you want it done by hand? So traditionally, for the first question in that homework, I used to just say, well, yeah, I kind of want it by hand because it's so easy to do, and I want to make sure you're plugging things in. But if you're really clear, like if you say to me that here's my Excel, I've got 6 rows, and this is my formula for the top cell in this column, and I just filled down this one using this formula, and this formula symbolically means this, that's fine with me. So I think it's only like I ask you to generate 5 numbers, so it's pretty easy to do by hand. But if you really would rather do it in Excel, if you make it super clear to me what formulas you used, then I'm okay with that. All right, any other questions or clarifications? This is a reminder that survey about when stage 2 happens is available until Friday night. So if you haven't taken care of that, go ahead and do that, and you'll get a lecture attendance credit for doing that. All right. Although I think I know what the answer is going to be already, but still like to get as many answers in as I can. Again, reminder, the arena competition, possibility for final project, totally optional, but entry forms due September 30th. If you're interested in the healthcare one and would like to try FlexSim instead of arena, its entries are due September 20th. So it's a lot sooner. I don't know all the details of the Semio competition or some of the other competitions, but happy to entertain those, but just be careful because a lot of times they do have their entries that are this early in the semester. Okay, so any other questions? Pretty clear where we're going with things? Looking online. Okay. All right. So like I was saying, so today we're now getting kind of into probability, and this is motivated by this idea of stochastic modeling. So this idea that we want our stochastic simulation models, and specifically focusing on discrete event system simulation models, to have realistic variation. We really want it on purpose. It's a feature, not a bug, that every time we run our simulation, we could get a different output, because every real system that we have, a hallway, an airport, a coffee shop, a bank, a factory, every day, that factory will have slightly different outputs, slightly different performance. We might do our best in terms of quality control to reduce the variation as much as possible, but there's going to be variation in the inputs. And so our job in quality control is to either reduce the variation in the inputs or build systems that are robust to that variation. But variation is something that we always have to deal with. And so if we want to test out our quality control ideas, then we need a system in the computer that also has realistic variation for us to see if we can start with a lot of variation and end with a very little amount of variation, that sort of thing. And so we really want realistic variation. But how to get realistic variation is not trivial. And so the approach we take in this class is a stochastic approach. And that stochastic approach means that even if the underlying system is not random, so in theory, you could actually go back, do the forensic science and see why everything happened, and it would have a deterministic cause. There's no quantum mechanics involved. But we're saying we don't care what the reality is. We can say at some level, if I drop a bunch of different details, then the results are going to look random. At an airport, it's going to look consistent with rolling a die. If it has enough sides and I weight the sides the right way, then the outcomes of the times between people arriving to an airport are going to be consistent with the right type of die roll. And so that idea of just using randomness for the purposes of modeling only, taking a guess or a conjecture just for the modeling purposes that the system is random, that's what we mean by stochastic modeling. And so when we refer to input modeling, that's us saying, how do we choose those probabilistic models that give us the right variation, that mimic realistic variation? So our systems will have variation. You push the real world into quality control spits out a distribution of parts. Here's failure time distributions or something like that, or how many widgets came out and were broken immediately. So we have some distribution that comes out of that. That's the output variation, but we have some input variation that comes in, and in input modeling is selecting the probabilistic models that go into those systems. And so the other view that I was saying here is we could say, well, if we had a purely deterministic model that didn't have any randomness involved in it, we know we would probably get something wrong. We would leave out some variables. Some of our variables would be the wrong value. We didn't account for temperature in this particular manufacturing process. And it turns out the manufacturing process is at least a little sensitive to temperature. And so some days when it's a little cooler, the process runs faster. When it's a little hotter, the process runs slower. And we could try to incorporate temperature in deterministically, but maybe we don't know that relationship. So in that case, we'd say, well, we're just going to pretend like temperature doesn't matter. But you'd say, well, but then you know that your system, your modeled system, is going to necessarily be different than the real system. So we're like, well, okay, so that uncertainty, we're going to say that ends up generating noise between our model and the real world. And we're going to then add in noise in our simulation model to try to make up that difference, to try to fill in that gap between the modeled version and the real version. So those are kind of the two perspectives we have here. We're either modeling the world as if it's random, or adding randomness is a way to deal with our uncertainty. Either way, we're putting in, these are kind of philosophical, which, what you're sort of saying you're doing, how you're justifying your use of randomness. But either way, we're using randomness. So in order for us to use randomness, we need to really be comfortable about probability, because probability is kind of the mathematical tool that has been developed for us to quantitatively handle randomness. And probability theory is a subset of a branch of mathematics called measure theory. And measure theory is a branch of mathematics which develops these things called measures. This little mu is an example of a measure, which effectively assign weight to things, to weight to sets. So in measure theory, you say I have a set of outcomes, and if I weigh that set on a scale, it has a certain weight, and if I weigh components of that set, then they have certain weights. And if I've constructed my measure properly, then when I add up all of the component weights, I should get the total weight of the set. That's the key feature of a so-called measure. And a probability measure is just a special case of that. So what we're going to be seeing here is I'm going to give a lot of weight-based interpretations for probability that help us to better conceptualize the curves that we're looking at. All right, so let's get some terminology out of the way. Just glancing online for any questions or stops. All right, so this term random variable that we're going to use a lot. This is sort of a problematic term because formally speaking, from a mathematical point of view, a random variable is neither random nor a variable. It's a deterministic function. So it's a function that maps a so-called space of outcomes to a so-called measurable space. And so outcomes are from the real world. They are mutually exclusive results of an experiment. So there's all of the different things that could happen if you ran an experiment. And the measure space is just something that helps us quantify those. And so they're usually we take the measure space in this class to be the real numbers. And so we're just mapping outcomes to real numbers. So as an example, the number of coins landing heads up. So the actual coins landing heads up, those are the outcomes. So I got a head, tail. So those are 3 heads and a tail. I can then map that to a random variable, which would be the number of coins that actually lands heads up. So in that head, tail, it would be 3. So that outcome, head, tail, maps to the number 3. And that mapping is what we refer to formally as the so-called random variable. And so the random variable here, we're going to refer to those outcomes, all of them together, as the sample space, sometimes with an omega. And we're going to refer if you take all of the outcomes in the sample space and look at all of the numbers that they map to, that set of numbers that they map to, we're going to call the range. And so the range of a random variable is all of the different ways an experiment could happen, map each one of them to the number value that the random variable maps to, and then that set of numbers is the range of the random variable. So formally, if you get sort of far enough in having to write proofs about probability or whatever, you'll write random variables with this long hand notation here, where you actually have to formally specify all of these things together. But because usually in classes like these, the measure space is almost always the reals, and the outcomes are usually specified somewhere else, we often just shorten it to X. And so when you're introduced to these things, we just say, well, X is a random variable. But at this point, we have to sort of start admitting that X isn't a variable. X is actually the shorthand for a function, which takes maps from outcomes to numbers. And you can have different mappings. So heads to tails, I can map a head to a 1, a tail to a 0, but I can also map a head to a 1, a tail to a -1. And so different mappings may have different consequences in in terms of what we think about in terms of how do we quantify the frequency of these outcomes. All right, so from there, for every outcome, we have to create, and it's unfortunate that we used to use this term, but this is just a traditional term, independent of this class, an event. So an event, in this case, is not a discrete event system event. An event in probability terms is just a set of outcomes. So you could say that, I could have heads, 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 tails. That's one outcome. I could have had heads, heads, tails, tails. That's another outcome. Those two together would be considered an event. If either one of those outcomes is the so-called event. Or I could define an event in terms of at least one heads. That is a bunch of outcomes together, all grouped together into a set called an event. And so I've got some examples here. Outcomes, like from a six-sided die, these are single outcomes, but each one of these events are a set of outcomes, where these first two events only have one outcome in them, but these last two events have a bunch of outcomes in them. And we have to define these events, because this is getting to that idea that we need to somehow have a way to weigh things that can be broken apart. And outcomes can't be broken apart, but events, because they have multiple outcomes in them, can be broken apart. And that's the reason why we have to have this thing called an event when we talk about probability. So when you talk about the probability of something, what you're actually asking for is the probability of a set of outcomes. That set might have only one outcome, or it might have multiple outcomes in it. So outcomes are the particular things that could happen in an experiment. Events are the things we actually measure, and events are sets of outcomes. So I think I have an example of this here. Well, okay, don't mess with these. Are the examples here. Are there questions about that distinction between outcomes and events? And again, this event is not the event we talk about with discrete event system simulations. This is just baggage from the measure theory that a set of outcomes is called an event. Okay. All right, now, once we have events, we can now weigh this bag of outcomes. And what do we use to weigh a bag of outcomes? That's a so-called probability measure, usually denoted with an uppercase P, lowercase r, upright. And a probability measure, like I said, is a scale that can weigh each one of these events. So this probability measure is going to be specially selected to have conservation of mass. So an event can be broken up because it is a set of outcomes. And if we take an event and create two sub-events, if we weigh those sub-events, which are just subsets of the event, then the total weight should add up to the weight of the whole event. So you could imagine lots of different mathematical functions that don't have that property. But if it is a probability measure, then it has that property. That's what makes it special, to be a probability measure. And that's kind of all that I'm saying here. But the one thing that makes it a probability measure and not just a measure is that the weight of the sample space omega is 1. So that the total outcome space, the sample space, that omega that was back here, the sample space itself is an event. It is every single thing that could possibly happen. And the probability of omega, the probability of that event, is always equal to 1. So this is like a scale that it's been normalized to what you're considering your universe of interest. And so if you weighed the universe, we're just going to arbitrarily say the universe is weighed 1. And then each one of us would then have a fraction of the universe's total weight. And that's where we get probability. That's the reason why probabilities always go up to 1 and no higher than 1, is that they have been defined so that this outcome space that you've defined ahead of time, the probability of the whole outcome space is always equal to 1. And that way the probability of any subset is going to be less than 1, because we use these fancy mathematical tools called measures. So if you take a theory in advanced statistics or probability or whatever, you'll learn to write measures. And when you write those measures, you have to make sure that they have these properties so that they are a measure and that their highest value is 1, and that guarantees that they're a probability measure. So those are properties that we can count on, that will always be there when we talk about probability. Any questions about this? It's a little abstract. Just trying to get all our terms out there so that we can connect a bunch of these things and in a rigorous way. Okay. All right, so we define the range. Remember, the range is just the set of the real numbers for which the outcomes map to. And now that we've numerically quantified the range is a numerical thing. Outcomes are just abstract objects in space. We don't, heads, tails. We don't really have a numerical handle on that, but the range we do. And so now we can start characterizing random variables by properties of their range. And so if the range is finite or countably infinite, then we refer to it as a discrete random variable. And again, it's another unfortunate collision between the class, the simulation class, and this probability, is that this discrete is a slightly different discrete than the discrete we talk about in terms of discrete event systems. That discrete has to do with discrete time events. This has to do with actually discrete outcomes. And so what we're saying here is that if the range here has a finite number of things in it, heads, tails. Well, heads is 0, tails is 1. So that means I only have 2 things in my range. Well, that's finite. So that means that is a discrete random variable. Alternatively, it could be infinite, but it has to be countably infinite. So I could say how many complaints could be registered at a particular company in a day. Well, it could be 0, could technically be unbounded. There's no way we can say that there's probably no way we can upper bound that. It probably won't ever be really, really high, but we still technically have to allow it to go pretty high, but we can count them. And so the fact that we can count them then makes them discrete. This will be contrasted with a continuous random variable where we can't count them. So like the temperature in this room, the different temperatures that you can get in this room can't be counted. So you can have a temperature of 77 degrees. You can have a temperature of 77.1 degrees and a temperature of 77 plus pi degrees. You can have any temperature you want from 77 up to whatever. And we can't count all of those possible outcomes. And so that's the distinction here. So discrete, you can count the range. And then continuous, as we'll see in a second, you can't count the range. And this is just another example of a discrete one here. Any questions about that distinction? What I mean by discrete or countably infinite? Okay, check online here. Okay. All right, so now that we've got these countable outcomes here, then we define as shorthand. If I say x is equal to xi, what we're saying is the event that corresponds to this particular numerical outcome. So there's an outcome out there. So it's the set of outcomes that correspond to this number xi. That's kind of what we're saying here formally. And so this is just basically saying the probability of one of those outcomes. And we can write this as a shorthand as this little p. So we only will use the little p for discrete random variables. So we never use a little probability measure when we talk about continuous random variables, because that will confuse it with the density. So if you're ever writing this down, or if I'm ever writing this down in a midterm or whatever, then a little script like this, a little script or a little p here, that will indicate that it is a discrete random variable. And it's just saying, what is the probability of this individual outcome? Each one of those probabilities, because they're probabilities, has to be greater than or equal to 0. And because of the probability measure having this property where you can cut everything up and measure it and add it all up together and it'll be equal to the whole space, the sum of all the probabilities across all the outcomes is equal to 1. So these are just properties we can always count on, so to speak, with a discrete random variable. We're going to refer to this little p function as the PMF, or the probability mass function. Mass here is analogous to probability. So, so when we actually talk about the weight of a set of events, we're sort of talking about the mass of those events. And so so these are kind of synonymous, probability and mass here. So a PMF, a probability mass function, is this little function P. And if we collect all the outcomes and their real line and their probability mass, we refer to that as the discrete probability distribution. So when we talk about the distribution, it's the collection of these, and each one of these is the PMF. So I'll use that term a lot, PMF, and then the related term, we're about to talk about PDF here throughout the rest of the class. All right, so any questions about these? Do these properties make sense? Every probability's got to be positive, but the sum of all the probabilities has to be exactly equal to 1 if you go over all of the possible outcomes. Okay, hopefully mainly review, but I just want to make sure we're all on the same page. So here's a question here. So here's an example where I have this range. So I have a die that has 6 sides. And so I'm just going to assign each side to a different number. So the number of dots corresponds to the particular number in the range. So 1 dot up to 6 dots. And so this is a weighted die. It's not a fair die. And so there are certain probabilities that are associated with each one of these. And so we've got that the rolling 6, getting 6 dots is 6 times as likely as getting 1 dot. And so I've got 1/21 versus 6/21. And so we're saying that the bottom row here is the probability mass function. And the 2 of these things together, the outcomes and the PMF together, we're calling the probability distribution. So the question here is, I just stated the important property here is that the number of dots is sort of, if you know how likely 1 dot is, you can multiply that by the number of dots to figure how likely the other dots are. And so that's the common sort of property here. Where does the divided by 21 come into play? So the numerators all mark that. So the numerators all come from this idea that if I roll a 3, well, 3's got 3 dots. And I know in this die, it has the property that the number of dots is going to just multiply however likely getting 1 dot is. So, so however likely 1 is, then at 3 times as that is what 3 is, and 6 times that is what 6 is. Where does the divided by 21 come into play? Yeah. That's right, right. So if I add up all of these together, 1 plus 2 plus 3 plus 4 plus 5 plus 6 is 21. So that little property that we saw on the last page here, that these all have to add up to 1, makes it actually easier when you're talking to a stakeholder to get kind of an idea of how to build the model from them, because they will say to you things like, well, we just want to make sure that people ordering refrigerators is twice as likely as people ordering toasters. And so you write that down, you say, okay, so refrigerators equals 2 times toasters or whatever. So you can write down all of these things. And then so if you're talking about an outcome for an order coming in, what's the possible outcome? Well, this might be refrigerator, this might be toaster. So you can kind of leave a placeholder in here. I could say, well, I'm just going to call toaster alpha and refrigerator is going to be 2 alpha or whatever. And in the end, you'll have, that the whole thing has to add up to 1. And so a lot of these alphas are effectively going to cancel out, or they're just going to be whatever the sum of the things in front of them are going to be. So in this case, the sum of the numerators are 21. So the alpha here is just 1/21. So so you don't have to specify to someone what the actual probability is. As long as somebody gives you the relative probability, it's usually easy to build these models because you know that it all has to add up to 1. So something to keep in mind. Those of you who end up going into a field where you use machine learning, you're probably going to encounter something called a softmax function, which is another thing where you've got to classify things into different groups, and it's got to give you probabilities of those different groups, and it does a normalization that's just like this. And so it's the ratio of one thing to another is more important than the actual probability, as you can always solve for the actual probability. It's kind of the little lesson I was trying to say here. And if we verify All the probabilities are greater than 0, good, and they all sum up to 1, which is what we were expecting. We're going to summarize these distributions with these little plots like this. When I plot a probability mass function, I'm always going to use these little pins. So these are called Dirac delta measures. You don't need to know that term, but I use them very deliberately. I will never plot a probability mass function as a step function, or I definitely won't interpolate in a probability mass function. So you can kind of visualize this as a pin sitting on the outcome with this amount of weight sitting on the tip of the pin. So this pin is very lightweight, this pin is very heavyweight, but all of the mass is located on that one particular outcome. And so for probability mass functions, we draw them like this with nothing in between. And this is really showing us that the only possible outcomes are 1 through 6, nothing in between. That's what makes them a mass function. And we can concentrate all their mass on these points. And that's why I like to make the pins here have pin heads that are solid, which really show that there's a mass sitting there. And this will help us discriminate between probability mass functions and probability density functions, where you won't see any of these pinheads here. It'll be a smooth line. So this is very deliberate how I got things plotted out here. All right, any questions about the discrete stuff before we transition to continuous? Hopefully most of that is review, maybe with a few extra things put on the end there just to make things a little bit more rigorous. But basically the same stuff we've hopefully seen before, doing combinatorics and things like that in 380 or 385. Okay. All right, so let's do a little attendance response just to wake everybody up. So this will be question 1 here. I'll put it in the chat as well. And the question here is, we'll say, we'll just say, what is the probability of the full sample space, which is omega? So if I were to say, take the probability measure, and I've got the event, which is the full sample space, omega, what's the probability of that? Okay. All right. So continuous random variables, this is pretty exciting, continuous random variables, because it's a little hard to wrap your head around. But I think once you do wrap your head around it, it provides a lot of interesting kind of perspectives when thinking about probability. So a continuous random variable, we characterize random variables by their range. So if the range of a continuous random variable is a collection of intervals on the real line, we refer to it as a continuous random variable. It doesn't have to be a single interval, it can be multiple intervals. It can be anything from 0 to 1, union anything from 2 to 3, union anything from 11 to 11.5. And those 3 intervals together, that union of intervals, would be a continuous random variable, even though there are gaps in between. And so a continuous random variable, again, it's got this continuum of possible outcomes. And because of that, in order for us to define weight, we have to kind of go to another level. This table right here, it exists in a continuum of space. It exists at 0, if I call this 0, and if I go back a foot, it exists everywhere from 0 to 1 foot, everywhere here. I can weigh the whole table. Like if I were just to roll this table out, if I can, I could weigh this entire table, call this 0, call this 1 or whatever, and that table would weigh something, whatever, 40 pounds or something like that. Then I could call that 1 if I wanted to and normalize it. Now, I've got this continuum here. I have to really think about, how do I define weight for a continuous thing? Because I can say, well, what is the weight at a particular point? And if I go to a particular point, a foot in, right here, and I slice it down there, if I took an infinitesimally small slice to say, what is the weight right there at a foot from the edge? that weight will always be 0 because it's an infinitesimally small thing. It's too thin for me to weigh. So I need some way to deal with this weight. Like, I need weight to exist somehow from here to the end of the table. I need weight to exist. But every time I take a slice of infinitesimally small slice of this and I put it on a scale, the smaller that slice gets, my weight goes to 0. So I can't somehow define the table as the sum of all the infinitesimally small slices, because every slice has 0 weight. So what do? Well, in mechanical engineering, we define density. We say that this table has density everywhere. It has a uniform density, and that density might be in pounds per square inch or pounds per inch, the linear density. So as I move an inch, I gain that. So if it, let's say if it was 1 pound per inch, every time I move an inch, I gain a pound. I move another inch, I gain another pound. So as I add another inch, I gain another pound. Now, the interesting thing about density is that you can have it's a different unit than weight. The density of the sun is extremely high, but I could have a tablespoon of the sun or a thimble of the sun or something even smaller than that of the sun, down to the point where the density, the number, whatever that number is numerically larger than the weight of that thimble. So even though the density of this table might be, imagine a table where there was where the end of this table was just really dense and everything else wasn't. And the end of this table is like 1,000 pounds per inch. But once you move an inch, the density dropped down, and then that density became a pound per inch. Well, the whole table might only be 30 pounds, even though the density near the edge is over 1,000 pounds per inch. They're different units. So that's what I'm trying to get here, is that when we learn about probability density, and this will be on the slide here in a second, probability density, that little f that you've seen here, does not have to be less than 1, because it is a probability density. It is a way that we are somehow allocating the 1 unit of probability in this continuum to everything in the continuum. So we can't define probability at a particular point. The probability at any point is always going to be 0. The weight at any point is always going to be 0. But we can say, if we move a full inch, how much weight do we add? If we move a full set of outcomes, how much probability do we add? And so the probability density can be greater than 1. The same way the table's density can be greater than the table's weight. All right, so let's see if we can make more sense of that. So I can have a probability density function like this one, and that, so I've got outcomes that exist from 0 to infinity. So on the whole half line, from 0 to infinity. It's just like here. Imagine this went to infinity. I've got outcomes that exist from 0 all the way to infinity, and everything in between. And so I can allocate a density to that the same way I allocate a density to the table. And instead of weighing a particular point, I weigh a set, basically a subinterval. So I say, what is the probability of the interval of outcomes from A to B? That's the same thing as saying, what is the weight of a little ribbon of this table from A to B? Take that ribbon out, I weigh the ribbon. And that is taking the integral of the density from A to B. The same way, if in mechanical engineering in a statics class or something like that, if you knew the density of this table, if you'd say, well, what's the weight from 1 foot to 2 foot? You could say, well, give me the density. Okay, I got the density. I'm going to integrate from 1 foot to 2 foot of that density, and I'll get the weight of that ribbon from 1 foot to 2 foot. It's identical. It's the same formulation. So, so that's kind of where probability density comes from. So that ends up giving us these properties, which look a little probability-like, but then get a little screwy and different over time here. So we know that the density has to be greater than 0. The density of a table has to be greater than 0. That makes a lot of sense. We know that the density has to be exactly equal to 0 if you're not in the range. Similarly with this table, if this table is our object of interest, the density off the table is got to be 0 on either side of it. So density, if you're not in the range or the so-called support of the random variable, your density's got to be equal to 0. Now, here's the thing that's different than probability mass. The integral over the range of the density has to equal to 1. But that doesn't mean the density has to be less than 1. The density itself can be greater than 1 because density has different units than probability. So a point of non-zero density has no mass. So that's the other thing too, is that like at any individual point, the weight of a point is 0, but the density at a point is non-zero. So there is a relationship between density and weight, between density and probability, but it's communicated through this integral operator. And so we can't directly compare those two units. So when somebody gives you a probability density, don't think of the density as a probability. It's things that are more dense are somehow more likely, but we can't directly say that because you have a probability density of 0.5, that outcome is 50% probable. It's not. You know, just because you have a density of 0.5 doesn't mean that point is 0.5 weight. All right, so that clear what I mean by the distinction between density and weight, or density and probability. It's a very mechanical interpretation, but again, that's probability all comes from measure theory. Measure theory was designed to deal with continuous things, weighing continuous things in the real world, and people just picked that up and then turned it into probability. All right, so got these examples here. I already mentioned this. Well, you know, taking A to B, there is a weight to this interval here, but there is no weight to this point. That's all I'm kind of saying here. So mentally, you can think of the probability density function as representing a block with a total weight of 1. And that block, you can either think of it being denser on this edge, or maybe it's uniform density, but the block is literally taller on this edge and narrower on this edge. And so when we're thinking about how to make sense of these outcomes, we can think about where is the weight concentrated. And so knowing how likely certain intervals are, we could say, well, over here, I've got more weight above this than over here. But any individual outcome has got a probability of 0. So if I threw a dart at this table, there's a 0 probability that I'm going to hit any individual point, but there's a 100% probability I'm going to hit the table, hopefully. I don't know, it's me, maybe not, but hopefully there's a 100% chance I hit the table, and a 50% probability I hit half the table, and so on and so forth. And that's what sort of communicating here. So I highly encourage you to take this kind of physical interpretation of probability density and probability mass as related to weight and density. All right, so example, X is a lifetime of a device that inspects cracks in a wing. So its range is the half line. It's everything from 0 to infinity. So it can be any non-negative value. So we're going to model it as an exponential random variable. And that exponential random variable, we have a parameter called a mean, which we'll talk about, of 2 years. And so the PDF, the probability density function, expressed in years, is a density, not a probability, of this thing right here. And so it just so happens that when I plug in X is equal to 0, this thing starts at 1/2. But there's no need for that density to start at 1/2. So if I change the mean here, then this density might start at 10 and then fall off much more quickly. All that matters is the area underneath is equal to 1. So then I want to know, what's the probability that it's going to fail between year 3 and year 4? I just take the integral of the density function between 3 and 4, and I'm just weighing that little block, kind of what we get there. And then if I want to, I can also plot the mean of this function here. And we're going to get to this in a second, what a mean means, but I hope you can see here that that point where the mean of this distribution is the point where if you were to build this distribution and set it on a little teeter-totter, it would balance right there. So that's what the meaning of a mean is it is the balance point of a probability density function or probability mass function. All right, so that's our example from continuous random variables. All right, any questions about the continuous stuff? Online or in class? Are these distinctions making sense? Does that make sense what I mean by density and weight, density and probability? Probability density, you should focus on the density, not the probability. Okay. All right. So in the homework D2 or whatever, I have you generate random variables from a probability density function whose density is greater than 1. A lot of times when I give these things on a homework, I'll get somebody asking me, did you make a mistake? Your probability density function is greater than 1. And no, I didn't. And so it's meant to be greater than 1. And so you'll get an example where you'll have to actually generate random variables from density functions where densities are greater than 1. What the heck does that mean? You'll see that. So, okay. All right, so we are going to make heavy use of the cumulative distribution function in this class, the CDF, and that CDF is just used. We usually use the capital F for it, maybe with a subscript to denote the variable we're using. And the capital F of X is the notation we use. It's defined as the probability that the random variable we're focusing on is less than or equal to whatever that little x is. So it's just a probability, but it's a probability of from negative infinity up to x, what's the weight that we accumulate there. So for a discrete random variable, we sum up all of the outcomes less than or equal to x, and we sum up their probabilities. And for a continuous random variable, we take the integral from negative infinity up to that of the density. That's all we mean by a CDF. CDFs have a really cool set of properties. And for one of them, f is a non-decreasing function. So if you go from f of a to f of b, if a is less than or equal to b, then f of a will be less than or equal to f of b. So that ends up being a really useful property. F is also bounded because f is a probability. Then as you go to infinity with its argument, as x go to infinity, it will go to 1 always. Likewise, if you go to negative infinity, it will go to 0 always. And so probability cumulative distribution functions tend to look S-shaped because they start at 0, they rise up, and then they hit 1. So they look like an S, S for Sam. So they can sometimes be aligned and sometimes kind of peter out, but generally most of these look kind of like an S shape. And they have the nice function property here that if I ask you for the probability of an interval and I've given you the CDF, all you have to do is subtract the CDF evaluated at the low end of the interval from the CDF evaluated at the high end of the interval. So if I give you a density function and a cumulative distribution function, which you can view as sort of the integral of the density function, you could bother doing the integral yourself of the density function, or you could ignore the density function and just plug in to the CDF because I've already done it for you. So these are some really useful properties that we use all the time when we deal with these CDFs. So an example of that for my discrete random variable, I've got 1 through 6, and notice that the CDF is solid and then it jumps, and then it's solid and then jumps. And these jumps I try to show with these dotted lines here. And so, and then these open circles means that it's not that at that point, it's the solid one at that point. And this is just trying to show this idea of probability mass, that once you go over outcome 1, you've just added a shot of mass. That pinhead of mass has been added, and that's what causes this stair-step routine here. So this is showing that I start at 0, I end at 1 as expected, but instead of getting my probability masses, then I've got these cumulative things here. So I start at 1 over 21, I add 2 over 21 to get 3 over 21, I add 3 over 21 to get 6 over 21, I add 4 to get 10, I add 5 to get 15, I add 6 to get 21, and that's how I get my CDF. And I've just plotted the CDF here instead of the PMF. So does that make sense? This CDF here. And the cool property here, the outcomes here, or the probabilities here are always from 0 to 1. So what we're going to see in an upcoming lecture, lecture E2, is that if I were to draw a random number between 0 and 1 and use the inverse CDF, I can then get an outcome out of my computer that will match my desired random variable. So one of the reasons we use CDFs a lot in this class is with the CDF, you can take a probability mass function you've decided is the right model for your system, turn it into a CDF. And once you have it as a CDF, then you can draw a random number between 0 and 1, which we all know how to do after that last lab 3. And you can turn any random number between 0 and 1 into any random variable that you want by just using it, pushing it through the inverse of your CDF. And we'll talk a lot more about that in lecture E2, but this is a preview of that. This is one of the reasons why we use CDFs so much in this class. All right, it works the same with a continuous variable as well. So here is the CDF for an exponential random variable. So it starts at 0, climbs up to 1, but it has no stair steps because it's a continuous random variable. And then likewise, if I wanted to draw an exponential, you may not know how to draw an exponential in Excel. Well, if you know how to take the inverse of this 1 minus e to the negative x over 2, so that's CDF, you can take the inverse of that CDF, then you just have Excel draw a number between 0 and 1, run it through the inverse, and it will give you an outcome that if you were to draw 1,000 of those outcomes and then take their histogram, the histogram would be consistent with an exponential. And so that is a way that we will end up getting, this is how we end up getting any distribution we want, even though the computer only provides us with one distribution. So that's where we're going, again, by lecture E2. All right, so any questions on all of this stuff? And then we only have like a couple of other formalities here. We're pretty much almost done here. I know it's a lot of listing stuff, just, you know, we're just kind of getting this kind of terminology and baggage out of the way before we can start doing interesting things. And so, you know, it's a little dull, but hopefully helps clarify some things. All right. So let's do another attendance question for kicks, just to wake everybody up. And the question here is, what is the value of a CDF evaluated at negative infinity? So every CDF evaluated at negative infinity has a particular value. What is that value? Okay. So for kicks for the class, not that question. So what about the other side of it? So can somebody tell me every CDF when evaluated at infinity has a value? What is that value? 1, that's right. So every CDF ends at 1. All right, so the other couple of things that we need to define are moments. And so the expected value, or the average, as you might say, but the expected value of a random variable is what we refer to as the center of mass of a distribution. Regardless of whether it's probability mass function or density function, we refer to the center of mass of either distribution as the expected value. So for a discrete random variable, it's defined like this. It's just the sum of the outcome times its probability, and then that sum over all outcomes. For a continuous random variable, it's the integral of the outcome times its density. And then that whole thing, the integral over all of that. You can kind of think of the density times dx. Those together are like a probability mass. So that's why it's kind of the same here. But but instead of a sum, you've got the integral. Does anybody happen to know where we get the integral sign? What is an integral? Like, why that symbol? Any guesses? Nobody? No guesses. It kind of looks like it could be musical, but there's something I think even more direct. So the integral is supposed to look like an elongated S for sum. So the integral is a sort of a fancy type of sum, like SUM, and so that's why this is kind of looks like an S here. So you're summing over infinitesimals, and so that's why they made this funny S. So this is a sigma, which is S. So discrete sums are a sigma, and so continuous sums are an elongated S. That's what an integral is. All right, so this is our definition of the expected value. If you were to take a statics class in mechanical engineering or whatever, this is identical to the definition you'd get for the center of mass, where this would be the mass of, if you have a bunch of kids sitting along a teeter-totter, each one of their weights, and where they sit on the teeter-totter, this would be their distance from the center of the teeter-totter. This would be the weight at that distance. If instead in statics, you knew the density of a table, then if you wanted to calculate the center of mass of the table, you would do the distance from the edge of the table times the density of the table, and you take that integral. So in both cases, you get the center of mass, which, like I said before, is the point at which if you had a triangle fulcrum, you could set that thing on top of, and it would balance right on top of that. So it really is the center of mass, just like in physics, it's the center of mass. We also will call it the mean. We'll use the Greek symbol mu, so mu sub x, and we also refer to it as the first moment of x. It's technically the first central moment of x. So this term moment, you'll see that. So that just means basically whenever you form one of these products between a distance and a value, a distance and a weight, then you generate what's called a moment. And so, you talk about a torque, if you put, if you've got a lever and you put a bunch of weight out at the end, then you generate a torque, which is also referred to as a moment, which is the distance of the lever times that weight. And so distance times weight gives you moment. And that's why we refer to this as the first moment. This is one way to define a moment, distance times weight. So, graphically, if I've got my probability density function, if you were to imagine this was a chunk of wood cut out of that was all uniform density, or was a 2x4 that, so just a flat piece of wood that happened to be denser on one end than it was on the other, either one of these works. For me, it's easier to think of a uniform density piece of wood that's cut out into this shape. Then this point will be the point at which that object would balance. So I've got a piece of cardboard in my office that I forgot to bring that I've cut out in the shape of this exponential, where I've drawn the balance point, and I can put it up on my finger and it'll sit there and balance. And so you can try that at home. If you cut this out just precisely enough, you can get these things to balance. And so really is meant to be the center of mass of the distribution. Now, the other moments that we talk about, there are, so that's the first moment. You can have second, third, fourth, nth order moments. And all of these moments are just going to be the same form, but you raise the distance to that power. So the second moment is the sum of x squared times p of x over all of the x's, or the integral of x squared times f of x over the whole range. And so the second moment is a quantity I'm going to show you how we can use. If we know how to generate a first moment mathematically, it's pretty easy to generate a second moment. And if you have all of these moments from the first moment through the infinity moment, then there's a bunch of different mathematical operations that you can do that that are sometimes that are easier to do with the moments than they are to do with the distributions themselves. So one example of that has to do with variance. And so the variance of a random variable is what we refer to as the second central moment. So what do we mean by central moment? What we mean by that is we take the random variable and we subtract its mean. That is what we mean by central. And it is a second moment because we take the expectation with the square. So an expectation with the square, that is a second moment. So expectation of x squared, that's the second moment. So the expectation of x minus its mean squared, that's the second central moment. So sometimes that term will be used instead of variance. So the variance of a random variable is that formula, and it just so happens that the variance of any random variable is just the second moment minus the square of the first moment. So a lot of times you might not know the variance ahead of time, but you might be able to look up in a table all of the moments of a distribution. And if you know all of the moments of a distribution, you can subtract off the first moment squared by the second moment, or mathematically, it might just be easier for you to do this calculation than it is to do this calculation. So it just is another way to conveniently do that. If we refer to the standard deviation, it's just the square root of the variance. It ends up taking the variance and puts it in the same units as the main random variable. We'll use the terminology sigma for standard deviation, or the notation sigma, and sigma squared for variance. All right, so hopefully some of this stuff is review, but I'm happy to take questions. So any questions about these moments? What we mean by these different terms? First moment is the mean. Second central moment is the variance. Square root of the variance is the standard deviation. The second moment, higher order moments, the second moment measures the spread of a distribution. The third moment is sort of how skewed it is, so how asymmetric it is. And so each moment sort of represents a different characteristic of the distribution. And so that's another way to kind of unpack a distribution, is to analyze its moments and compare them to each other. Okay. So any questions? And actually somebody online said it looks like an S. It's because of the Riemann sum I got. So yes, so somebody online got it, that the elongated S is it's exactly that. It comes from being a sum over infinitesimals. So thank you for that. I'm sorry I didn't see that answer earlier. All right. So where are we going from here? So that was our big sort of background and probability. So we're going to then fold that into some queuing theory, because we're interested in how things arrive over time. So it's naturally, queuing theory is sort of the combination of thinking about probability in space with probability in time. We're then going to sort of talk about what are the most common distributions that we're going to use to model things. So when do I use a normal? When do I use an exponential? When do I use a Weibull, et cetera? And so on and so forth. So that's kind of what we're kind of going for here. So that's all I've got for you today. So I'm happy to take any questions. Otherwise, here's your last attendance question. And this question is, what is the second central moment? What's another name for? What is another name for the second central moment of a distribution? And that's all I've got for you. So otherwise, feel free to go. If you have any questions, happy to stick around to take those. And any questions online? All right, looks like everyone's dropping off. So I will close the meeting, or at least stop the recording for now.